assuming we have collected this data and now we want to test whether we do see this difference in the number of cotyledons between the first generation and the second generation. And in this case, I'm just showing this. This is an abstract graph where we can pretend that we are measuring this quantitative trait for generation 1 and generation 2. And then the question is, what is the evidence for directional selection? What is it that we can see from the data? And the first thing in mind is that we have this distance between the means. So if we were to calculate the average number of cotyledons in the first generation and the average number of cotyledons in the second generation, and we see that there is this gap, there is this distance between the means, then that could give us some evidence visually that there is this shift. So the second generation is shifting towards more cotyledons than the first generation. But of course, a graph is nice to visualize it, but it's not an actual test. And if we want to know a test, we need to account for what is really signal and what is noise. And like I said, the evidence that we have from the data is this distance and this gap between the means. So if you could move to the next slide, please, thank you. And then the question is, if I see this gap, if it's quite big, perhaps we can say we have strong evidence, but if it's a smaller gap, can we really claim directional selection, or if this is just noise in our data? And this is why I always ask, well, a plot is a very good way to visualize the information that we have, but ideally we want to accompany a graph with a statistical test. So the standard test that we have for this type of comparison is the t-test. And in the t-test we have, as in the slide, we have two means that we're comparing, and the t-test is actually calculating the differences between these two means, so that if our test statistics, the t-test, is really close to 0, for example, can you move to the next slide, Julie, please? Yes. If this test statistics is very close to 0, that means that we really don't see any evidence of a difference in mean. So that will agree with a statistical null hypothesis. So just to remind people, the null hypothesis is usually the case where we have no signal. So in this case, putting in these terms, it means that there is no difference in means. So our null hypothesis says we don't have any difference in the means of trait 1 and trait 2. Back to our case, it would be there is no difference in the average number of cotyledons in generation 1 compared to generation 2. That's the null hypothesis. If when we calculate the t-test, which is this this formula, if this is very close to 0, that it's agreeing with the null hypothesis that there is no evidence of directional selection. But if, on the contrary, this t-statistics is either too big or too small, depending on which side you're making the difference of, then we have evidence for directional selection. We can reject the null hypothesis and claim that with our data, we see evidence of this shift. Now, the t-test has two main assumptions, and that is that our trait is normally distributed. So I'm plotting these as really nice normal distributions for the traits, and that both populations, generation 1, generation 2, they have the same variance. So it's not that you have a really fat curve compared to a very skinny one. They have similar variances. These are the two main assumptions. So when we want to go back to our data and ask the question, can I use our t-test, we have to compare these two assumptions. So again, with our data, Katie already showed this, we are counting the number of cotyledons of the plants that we have, and we record whether they are the parent generation or generation 1, or whether they are the offspring generation or generation 2. And I always like to point, as the field of data science keeps growing and growing, the way we store our data and record our data begins to matter a lot more. So there is this paper here that I put in the corner. It's an open source paper, anyone can see it, and it's from another professor here at UW-Madison. How do we organize data in spreadsheets in a way that makes it easier for us to analyze later on with statistical tests? So I just wanted to point at this resource in the future. If we're going to be collecting data in spreadsheets, which I think is what we should do, it's always good to know what those best practices are. Okay, so this is how our data looks like. So again, we want to start with some visualization. Here, this is perhaps a weird plot. Perhaps people are not as familiar as them as with the densities plot that I showed before. But I like to plot this just to see that specific example. I'm just going to go over the specific details. So in the x-axis, I have the two populations, the parents and the offspring. And I'm counting the number of cotyledons that I have. So each dot in this plot represents a plant. And they should all be actually collapsed one on top of the other. There are not 2.2 cotyledons. There are either 2 or 3 or 4. But I'm spreading them out a little bit so that we can see how many plants fall on each of these categories, so that we can see that the majority of the plants in the parent population have 2 cotyledons, or generation 1, and we see this shift so that the majority of the plants in the offspring population now have 3 cotyledons. And one thing that I should point out is that these dots, they are transparent. So if the color is very solid, it's because there are many dots on top of each other. So if it is very solid, that means there are a lot more plants on this group. So we see that this more solid, the red color here, around 2 cotyledons for the parents, and in the blue for the offspring, it's concentrated on 3 cotyledons. So at least visually, we can see that there is this shift. We have evidence from this plot. And lastly, one thing that I can point from here is that if you look at the 4 cotyledons level, you will see that for the parents population, there are just a handful of plants with 4 cotyledons, whereas in the offspring population, you have a lot more dots in there. So visualizing data, it's always a good idea from my perspective. I'm using R and ggplot to create these plots, but I will show you also the web app that we have, that we've been working on for people to generate this type of plots. And then the next step is that if we want to actually plot the densities that I showed for the t-test, we can see that they're not really normal. So in this case, for the plot here on the left, we have in blue the density corresponding to the offspring, or generation 2, and in red the population for the parents, or generation 1. And we see that these are multimodal, so they have peaks. It's not like a normal, standard normal that has just one peak and it's very smooth. And so this is clearly violating the assumption from the t-test that we need to have a normally distributed trait, because this has different peaks. And the reason for that is because we are not really quantifying a continuous measure. So if we were measuring, for example, height of a plant, then we do have 2, 2.1, 2.5. We have the whole range of numbers, but we are counting number of cotyledons. So we either have 2 or 3 or 4, nothing in between. There are gaps in the distribution of our trait. And that's why we have these peaks. So in theory, we want to compare the means of the 2 traits with a t-test. But now that we look at our data, we think maybe this data does not really satisfy the assumptions of the standard t-test. And I bring this example just to clarify that the data analysis part is also a process. It's not just a straight line of steps. So there's always a lot of, there's room for changing the type of analysis that we want to do depending on the trait. So in this case, what we can do, there are basically 2 options. So we can either use a fancier t-test that exists that does not require normality on the trait. It's called the Wilcoxon-Mann-Whitney test. We could do that. And it's just like a t-test. We're also comparing 2 distributions of traits, but we don't have the assumption of normality. Or more simpler than that could be, or more simple, or simpler, I'm sorry, than that could be, instead of having the counts of cotyledons, why don't we just create categories? So we say the plant is either a dicot or a polycot. Instead of counting how many leaves, well, we have to count them obviously to decide, but instead of having the counts as our trait, we're gonna have whether they are a dicot or a polycot. And then we do a chi-square, so which is is simpler because this is more standard type of analysis. So let's just focus on the chi-square, which I think would be easier. And for us to do this, if you remember the chi-square, we need to count how many dicots we have and how many polycots we have in each of the populations, the parents and the offspring. So this is the table that I show here on the left. And again, I like to visualize things, so we can visualize these groups it's called a mosaic plot on the right. And if the parents, they have the same proportions of dicots and polycots, that would mean there is no selection. They have exactly the same proportions. We would expect to see on this plot that they are equally, like the proportion, they are like exactly the same blocks. But we don't see that. We see that, for example, the parent populations, the majority of those plants are dicots compared to the offspring, where the majority of them are polycots. So we do see this difference in proportions just from the graph. But we want to complement, like I said, the graph with a test, which is the chi-square test. So if you remember this, the test statistics for the chi-square is simply we are doing the observed minus expected square divided by expected and summing over all these things. And the question is always, what are the expected, right? Where are the expected number coming from? Julie, do you mind changing to the next slide? Thank you. The expected values, they are connected to our null hypothesis. So to know where are the expected values coming from, okay, I have to think, what is my null hypothesis? And in this case, the null hypothesis means that there are no difference in proportions between dicots and polycots in the parents and offspring population. Because, like I said, the null hypothesis is usually there is no signal. And if we had a specific proportions that we would expect, for example, for a Mendelian trait, you would expect certain proportions. Those could be your expected values because you're expecting to see those proportions. In this case, we don't know what's the proportion that we would expect, but we know that we expect them to be the same. If there is no selection, then the proportions in the parent and in the offspring should be the same. So that's what we would expect under the null hypothesis. So thank you. In order to do that, we need to add, as you probably remember, add the number of total dicots, the number of total polycots, and the total number of plants that we have in both populations. And yes, so if we want to know what's the proportion that I would expect, we pretend that we don't know that there are two different populations, and we just count the proportion of dicots and the proportions of polycots as a group, like all combined. So in this case, we will focus, the proportion of dicots are just 2437 divided by the grand total, which give us roughly 43%, 43.6%. And the polycots have a proportion of 56.4%. And this is what I would expect without looking at the generations. So I'm not splitting by generations. If I just count how many dicots, how many polycots, and I count what's the proportion of each of these two groups, if the null hypothesis is true, there is no difference in these proportions, then I would expect to see these same proportions in the parents and in the offspring. So I would go back to, yep, one more, please. Yes. So since I observed 2557 plants in first generation, I would expect 43% of them to be dicots. So if I multiply 2556 times 0.436, I get 1115.3. This is what I would expect to see if I get that same proportion of dicots. And this is where perhaps you remember the formula where it's coming from, total rows, total number of columns divided by the grand total. That's where it's coming from. It's just the proportion that you are fixing. You want that fixed proportion of dicots. And then we do the same for the polycots. So for that parent population, we would expect 56% roughly to be polycots under the null hypothesis. And then we fill the expected on the offspring as well. And then we compare to what we are actually observing. So just repeating this one last time, we would expect to see no differences. So we calculate those expected values and we input them in our formula for the chi-square that will give us the gigantic number. So if you remember your chi-square table, I mean, has a so small p-value that you're really rejecting the null hypothesis that there is no difference between the proportions. And if you're rejecting this null hypothesis, back to our case, what we're really saying is we do see evidence of directional selection in this case.